Quick revision video on the anomalous properties of water. So we'll start with the essentials. Water has three anomalous or unusual properties. So the first one is it has a higher boiling point than expected. It has surface tension and it has a higher density than the solid state. So water has a higher density than ice. And all of these anomalous properties are due to hydrogen bonding. So we're just going to take each anomalous property in turn and go into the detail as to why it occurs. So starting with higher boiling point than expected, we've got three H2O molecules on this diagram here. So we're just going to explain why we've got the hydrogen bonds between the molecules, and obviously I won't explain it again on the other two. So we've got a dipole across the OH bond. Oxygen's slightly negative because it's more electronegative than the hydrogen. Got lone pairs on the oxygen, and the hydrogen bond is shown as an attractive force between the lone pair on the oxygen and the hydrogen of a neighbouring H2O molecule. So the higher boiling point is due to the fact that extra energy is required to overcome these relatively strong hydrogen bonds between the molecules. So to boil water, we've got to overcome these hydrogen bonds. So just to put this in some context as to how unusual this is, if we take the H2O molecule, it's got an MR of 18, we know the boiling point of H2O water is 100 degrees C. Well, if you look at the hydride of the group 6 atom directly below oxygen, so hydrogen sulfide, that's got an MR almost double of H2O, 34.1. The boiling point of hydrogen sulfide is minus 60 degrees C. Now, you would expect that a heavier molecule would require more energy to boil than a lighter one, but it's not the case. So if we look at the bonding diagram for hydrogen sulfide, virtually identical diagram, but because this is a sulfur now, then this is not a hydrogen bond. This is a permanent dipole force. And these are relatively weaker than the hydrogen bond. So less energy would be needed to overcome the force between these molecules compared to the hydrogen bonds that are attracting the water molecules. So hydrogen bonds are stronger than permanent dipole forces, so more energy is needed to overcome and separate the H2O molecules. So if we move on to surface tension now, so we've got a picture there of an insect that's able to actually walk on the surface of water. The reason that's possible is because of water's unusual property of surface tension. Obviously that's due to hydrogen bonds. So the water molecules are attracted to each other by those relatively strong hydrogen bonds. There's that diagram again. So if we just think about what's going on here, so we've got the water at the surface, these H2Os here, and then this is what we would class as the bulk liquid, so under the surface. The water molecules in the bulk of the liquid experience a net zero force because basically all the attractive forces cancel each other out. However, if you think about the water molecules at the surface, they don't have anything above them, so there's a net inward attraction on those water molecules at the surface, which means they resist, the attractive forces resist being broken, which is what creates this surface tension effect. And the final anomalous property, water has a higher density than ice. So density of ice, for your information, is 0.917 grams per cubic centimetre. Density of water, I'm sure you already knew, was 1 gram per cubic centimetre. So as water freezes, the hydrogen bonds actually extend and push the water molecules apart and form what's called an open lattice structure. So I've got this diagram to refer to now. So if we start with the liquid water, the hydrogen bonds are quite short, and so the H2O molecules are quite close together. When it freezes and turns to ice, the hydrogen bonds actually extend and you get this regular lattice structure forming. But because the hydrogen bonds are longer, it's classed as an open lattice. And what that does is it gives the same mass of water, when it freezes, it actually has a higher volume because the molecules are further apart. So if you think about how density is calculated, mass divided by volume, if you've got the same mass of H2O and you freeze it, it's going to have a higher volume, so when you divide by that greater volume, the density goes down.